Oh, hey guys, what's up? Eddie Alho here with KissAnalog.com. Hey, you know what I'm doing? I'm doing some interconnect testing. You know, I've done some other tests, right? I've done some tests that show that across the bandwidth, audio band, even beyond, they don't make a difference. I've gone to the really inexpensive speaker wire, trying to look for it. Got one right here, to this real expensive silver wire Kimber cable, and you couldn't tell the difference really. I mean, they were just flat, and so yeah, that didn't show anything at all. And so I thought, well, one of the things I always thought about interconnects is the importance of the shielding, because you got all the wires in the back and all the different interconnects crossing over. If you don't do a good job of cable management, keeping them nice and clean, away from power cords especially, and all this kind of stuff, I thought, that's what you want to do. But if you don't, then maybe a shielded cable would be the way to go. Well, I've got those nice inexpensive shielded cables, but I also have these expensive ones. So I thought, well, I'm going to start off with the cheap speaker wire, the one I made out of this stuff, okay? And if you saw the last video, if you didn't, I'm going to put the link down below. But, for some audio files, they might be kind of disappointed that there wasn't some difference. I'm trying to look to see if there's anything at all. So I'm really looking into this because, I did buy these expensive cables and I did buy silver solder. I was a believer at one time, and I hate to call them the believers versus the science guys, because they like to call us the science guys. But, it's the same engineers or science guys who designed the amplifiers that audiophiles listen to, and they seem to trust us to build amplifiers and preamplifiers and DACs and all kinds of stuff, but then they don't seem to trust us when it comes to cables. Anyway, I'm running some tests, okay? And what I'm going to do is, I've got this power supply back here that can do a dimmer function, that really noisy AC. When you want to dim your lights, well, you don't have a voltage regulator. Well, you kind of do. What you do is you turn on and off some special types of transistors that are called thyristors, and they turn on, they wait, and then they turn on, they show the sine wave, and then they turn off a little bit sooner. That way you only get a portion of your sine wave going to your light, so your light looks dimmer, because some of the voltage didn't get there. But they cause horrendous noise because those sharp edges. Whenever you have sharp edges, you got a lot of noise. And the current just shoots up, and then it does this kind of sinusoidal wave for part of it, and then it turns off. And then it's flat, and then all of a sudden it gets turned on again abruptly, right? So it's, like a Class B amplifier where you have the flatness in between. It's like that, but it's even way worse because of the only portion of the sine wave you're using, right? So what I'm going to do is take my power cord from my power supply and wrap it around the interconnect, okay? And then, so the interconnect will come from the Quant Asylum over to the input of this IEMA A07 amplifier, okay? And we're going to try to couple in some noise from this power supply. We're going to see if we can actually, couple it in. We're going to, by making basically a transformer, we're going to take the two wires, tie them together. We're not going to go around a core, so it's like an air core inductor, but we're going to wrap them together and see if we can induce some noise, okay? And yeah, so let's go ahead and try that out. I've been running some tests back there, so I'm going to come over, show you the setup. I've got things connected. I'm going to show you the power supply. I'm going to show you what the waveform looks like on the mix-sig. I got some mix-sig differential probes. I got a mix-sig differential, a current probe back here too, to see the current going into the load resistor. And so we're gonna really look to see if we can find something. All right, let's do it. All right, guys. So let me show you the setup. These leads right here, the power leads, are coming from my power supply. I'm going to show you that in a moment. I'm going to show you that setup. and it's coming in here, and I just popped this off. But anyway, it's going to go through these alligators, okay? And then down here, I got my, this is a Boldy 100. We won't be using that for this one, but we'll use this Quant Asylum. And the output of the Quant Asylum has a speaker wire, okay? And it's twisted in this load wire. So these wires here, these clamps, I'm going to re-clip that on there. But the current is going to come from my power through here over, and I can't pick it up right now because it's really hot. You see this resistor hanging off there, that green resistor? So it's hanging off that resistor, okay? I'm just going to send current to that resistor. But the interconnect, my interconnect here, the one I just made with speaker wire, it's wrapped around the wire to that resistor, okay? And then it comes over here, and then through this wire, it comes into the amplifier, okay? So we're going to try to see if we can get some of that dimmer, nasty waveform induced, coupled into our nice high-end speaker wire interconnect, okay? So we're going to see what we can get. Okay, so let me go show you the power supply setup, and then I'll show you the scope setup so we can see what that waveform looks like. All right, but let me finish showing the setup here. So the output of the amplifier has these wires right here, okay? So we're going to come into the Quant Asylum and see what the output looks like. But the output is going to these big old 200 watt 8 ohm resistor loads back here, okay? So, all right, so, and then also I have a current probe, the MIG-SIG current probe back here, okay? So then I can see what the current looks like coming out into the load, all right? There we go. All right, so we'll see what the signal looks like that's coupled into my high-end interconnect coming into the IEMA, and we'll also look at the output. So we'll look at input to output to see what the Quant Asylum can pick up. And then also I'll use the current probe on the MIG-SIG just to see what that waveform looks like. Okay guys, so I just kind of wanted to show you where things are positioned on the bench. Here's the power supply set up for dimmer. I'm going to show you a close up of that. We got the MIG-SIG down here. So let me zoom in on this power supply to show you the setup. All right, guys, so here's a close-up of the power supply. Now, it's set up for dimmer function. You know, the dimmer is, you have 120 volts, right? Here in the US, 60 hertz. But if you want to dim the lights, you still have that voltage. So what you do is you only turn on the waveform to the light at a part of it. So it's on and then it's off. I'll show you that on the scope in a minute. But we're going to set it for 30 volts. And here, let me just turn it on. And it's 2.34 amps peak and 1.6 amps continuous, okay? Now, the thing is, it's 47 VA, so it's about 47 watts per setting. So, you know, that's a decent amount of power, and it's making that resistor really hot, so I can't leave it on too long. But I just want to show you this setup, okay? Let's go look at the oscilloscope. All right, guys, so what I did is I chose one of these ceramic resistors. It's kind of a flat one. It's a 91 watt. It's kind of interesting wattage rating, but 18 ohms, okay? So it just happened to be something I had. I thought it was a good one to pull some wattage so we can get some current. All right, so this is the noisy dimmer wave shape. It's off, and then it starts going sinusoidal, and then right about here it just drops off. So that's a straight line, then it's straight again, and then sinusoidal, and it repeats. And so all these square waveforms are causing lots of distortion. Let's go look at the FFT on this just to see what that looks like. Now, you know what? One thing about FFT, it likes to have a lot of waveforms. So we'll collect a bunch of waveforms here. Okay, and then we'll hit the FFT on. Okay, we come down here, do the math function for the FFT. All right, guys, now we got all these waveforms captured, and so we'll do some math, and then look at the spikes. Now, what I can do is come down to channel 1. I love the MIG-SIG scope, easy to work with, And then we'll move the FFT right over this way. Okay. All right, guys. So I got minus 70 dB down here. Okay. And so we have 0 dB right here where you see the little M, then 10, 20, 30 dB. So look at all this noise. Now here, let me get the cursors up. And okay, well, that one landed right on. Well, actually, let's see. Let me just move that over to one of these. Now, what I see is each one of these spikes looks like it's actually made up of several spikes. So I think there's just a lot of noise going on here, just a crazy amount of noise. But that is, what is that? That's about 120 hertz. It says 118, but I'm sure if I got them perfect, it'd be 120 hertz. So 60 hertz waveform. And so there's lots of frequencies in between, but these big ones are 120 hertz apart. So that's pretty interesting, right? Okay, guys, so the generator, it puts out this 1 kilohertz, and then it recycles and it kind of pulses, so you'll see it pulsing on and off. I don't know how to make it stay on just continuous, but that's the way it works. So when it drops back down, it takes a measurement. But okay, so right now it's 0.03% THD, and THD plus N is, it goes 0.035, like you can round it up to 0.035, right? So 0.031 maybe, and 0.035, okay? And then signal noise, 0.031, let's call it 0.035, and 76.8, okay? So I'm going to wait until it drops back down again. Now look, we're getting a continuous signal. Geez, I don't know what the heck. Okay, so I'm going to go ahead and turn, okay, there it goes. When it drops back down and we get the readings like right now, I'm going to turn on the power supply, okay? So we're heating up my resistor. Did you guys see anything change at all? 0.031, 0.035. We got to wait for it to recycle again. 0.031, 0.035. Geez. Yeah, it's kind of funny how sometimes it cycles more. 76.8. So anyway, also the spikes here, if we could save that, and then we could save it with and without, you could see, I don't see any difference, okay? I just turned it off. Did you see them drop? Nope. Looks like no difference at all to me, which I was actually surprised. I thought we'd see more. All right, guys, we're going to do a test where we look at the THD, the total harmonic distortion, and the THD plus N, plus the noise. So not just harmonics of whatever signal is going in, but all the noise around it, okay? And we're going to do it at 1 watt and 2 watts. In the video, I kind of jumped in here because I forgot to, I didn't know what the values were because I moved the potentiometer here, the knob, the volume knob, and I kind of messed it up during the test. So just jumped in to let you know what we're going to do. All right, let's do it. So I also did the THD across the frequencies, okay? So we could just see, well, maybe at some frequency, maybe at a, you know, because the noise is coming at 120 hertz, maybe 120 hertz is worse. So maybe it'll beat against that, and, you know, maybe 60 hertz or some harmonic, or, you know, of that. All right, guys, so let's take a look at this graph. Now, you know, what I did is I set it for a couple power levels. You know, I'll check because I kind of moved around the pot and check, but I was trying to do 2 low power levels, thinking that if I did a high power level, that might hide the noise. So I was trying to do low power levels so that any noise, you know, that signal to noise ratio, right? If your signal is even higher and your noise is just what it is, then you're going to hide it. So I was trying to do low signals to give a better chance for some kind of noise input, but let's just take a look, okay? All right, so what you see here is this graph with the signal right here at the end. That's the last measurement it took, and then it just kind of freezes, okay? So I can give I can get the power level from that. But anyway, let me pull up the waveforms, okay? Okay, I just stretched out that picture a little bit. And these three peaks here, just ignore them. If I took I'd have to take the measurement again. This measurement takes a few minutes to do, and the resistors get pretty hot. But these are just random measurements whenever you see these little peaks. This curve is the signal, okay? And what you're going to see is the first two on the left are without the dimmer on, okay? So minus 2.5 dB and 0, which doesn't really mean anything. It depends on where I have the pot set, right? So anyway, I didn't move the potentiometer, didn't touch anything on the IEMA. I just turned on the dimmer and then reran the test. And so that was these two. So same thing, the low minus 2.5, minus 2.5 is both with the blue. And you can see a little separation here, but it's probably like these two blue points. It's probably just a bad measurement. But yeah, you can see how the blue is just on top of the other blue. Right through here, there's a little heavier line, but they look like they're right on top. I don't know if that's anything at all. And then they ramp up, so the THD does kind of come up in this amplifier at the higher frequencies, and it does have this shape for some reason. But anyway, so they duplicate each other, right? Same thing with the green. The higher power output level, it just duplicated too. And this anomaly, this green one came from the first run, and these two blue ones came from the second run. So you can tell they're anomalies because they didn't happen both times. So, you know, with each run. So you can see the blue line here, and there's a green line down inside here. So yeah, I could rerun this just to show that. But yeah, the point is in either case, when the current for the dimmer was running through the load, about 47 watts, it didn't do anything, okay? All right, can't help myself. We did the 1 watt and 2 watt. We're going to do 3 more because I want to do a little bit higher wattage. I'm going to go around just over 5 watts. I feel like doing the low levels, we're putting low level signals into the amplifier, so that's the best opportunity to get any noise in it. Well, I mean, the noise is going to be generated into it anyway, but what I mean is the signal to noise ratio should be closer together if there's any noise. If I put a big signal and put more power out, then the noise just gets lost in the noise. So anyway, there we go. That's the logic, and let's go ahead and do it. All right, guys, so there's 3 different power levels, and all the way down to 1.7 watts, 3 watts, and 5.4 watts. And I first did just like the last test. I did them without the power supply on, without the dimmer power current going through the cable. And then I turned on the dimmer and repeated the test. And there is no difference in THD plus noise. So no extra noise that it is picking up in the audio band at least, right? And none that I could see on the spectrum either. So there you go. So there you go, guys. I was prepared to try a bunch of the shielded cables and all that stuff. An unshielded cable, they're not even twisted. They're just, zip cord, right? They're just side by side, which actually is a good way to do it. It's the next best to twisting them, because at least the fields for the current leaving, the current coming back, this way, the fields on one's going this way, the other one's going this way, they cancel, right? So yeah, that's it, guys. And there was I counted 5 turns between from here to here, and then I have that little, I have this little cable, this extender that kind of takes the single, that takes these 2 wires here and puts them into RCA jacks that plug in. So that part wasn't twisted, but there's 5, 1, 2, 3, 4, 5. There's 5 turn, maybe even 6 turns, and they're pretty tight, except for here at the ends, but it's pretty tightly wound. And I was surprised. I thought I'd see some pickup, because I thought, hey look, there's a little bit of pickup, and when I use any one of these other shielded ones, it goes away. Turns out, no pickup. So let me know if you guys want to see me do some of these other power cables like this real expensive Kimber one. I've got some, you know, the cables I did before. I don't mind doing it. If you guys are interested, leave your comments down below. If I get like 10 comments saying to do it, I'll do them. But otherwise, if there's only one of you out there that cares to comment, then maybe it's just not worth it. But yeah, guys, I really thought interconnect shielding would be one reason to get at least a shielded interconnect. But man, it doesn't even seem like it matters. And I mean, this 91 watt resistor is getting pretty hot, so I had to put that fan on it because it's about a 5-minute test, I think it is. I didn't time it, but seems like it's about that much time. And that resistor gets really hot just after a couple minutes. So 40-something watts, you know, that whole 50% derating resistor thing, obviously that doesn't work. It works, but it makes your resistor super hot. So if you don't mind a resistor running at 70C or above, then derate at 50% like they teach in school. Otherwise, derate resistors only use about 25, maybe 30% of the rated power. So that's my little extra pro tip hidden there. So there you go, guys. Now, I guess I'm not sure what else to do with the interconnects. I thought this test would be one that would show some difference. So it looks like we're, I mean, God, yeah, I'm actually a little baffled, guys, because I was really prepared to do a bunch of cables here. But I thought I'd start off with the worst case just to see how much better it got with each other cable. But looks great. No difference. No extra distortion picked up. And, you know, this is 60 hertz, 120 hertz. That's the easiest lower frequencies, you know, with a decent amount of power inducing some kind of field. High frequency noise, it's less energy because it's smaller frequencies, right? It's just like, you know, when you look at the energy underneath, you know, so when you look at the energy at high frequencies, there's just not much energy there. That's why filtering for high frequency, the inductors and capacitors are all very small because not a lot of energy there. And it's a lot easier to filter that stuff. So this low frequency stuff, especially, this is the kind of thing that you would find, you know, behind all your equipment is the 60 hertz power, right? Well, here in the US, 50 hertz somewhere else, right? But anyway, dimmer switches are thought to be notoriously noisy, but didn't look like it made any difference here. I mean, I was up to 50 watts. You guys want me to go 200 watts? Is that going to make a difference? You got to get some more resistors to do that. But I was also doing a small signal on the IEMA. So I was given basically the best case chance to have the worst case signal to noise ratio between noise and my small signal. Didn't seem to turn out that way. So give me your comments below. Let me know what you guys think. Again, it just seems like cables just do not matter. And our equipment is far more sophisticated than our hearing is. Sorry, it's true. So we can see things that we can't hear. I can prove that I can show things outside the hearing range that you can't hear. But no one can prove that they can hear anything that we can't measure. That's never been proven. So if it has been, let me know. I've searched, tried to find stuff, and I'm going to do a rant about this because I can feel one coming up. So thanks for watching, guys. Really appreciate it. And I'm going to get back to testing amplifiers. I got a bunch of amplifiers, so I got to crank on these things. I'm just trying to find the best way to test, and I got all wrapped up in this because I wanted to make sure the cables I was using to test and my measurement cables were not introducing any noise or causing any measurement errors or anything like that, which I've kind of shown you guys that that's not the case either. So let's move forward. Thanks for watching. And 2 big thumbs up to my patrons. Oh, appreciate you guys, the ones that are still hanging in there. really appreciate that. 2 big thumbs up to my members of my channel for hanging in there too. Yeah, lost people, tough times. So yeah, really appreciate the guys that are hanging in there. So thanks a lot. We'll see you next time.